In the spring of 1975, in a design bureau attached to the Česká zbrojovka factory in Uherský Brod, Czechoslovakia, a steel frame sat on a workbench under fluorescent light. It was not finished. The slide rails ran along the inside of the frame, not the outside, creating a channel that looked inverted compared to every standard sidearm in production. Josef Koucký, the lead engineer, had spent months explaining this configuration to skeptical colleagues who believed it violated fundamental principles of mechanical architecture. The object was a response to a problem that had no obvious solution. The Czechoslovak services needed a modern tool to replace aging designs, but the specifications were contradictory. High capacity, compact dimensions, reliable operation under field conditions, and manufacturability within the constraints of a state-run factory operating behind the Iron Curtain. Western designs, like the Browning High Power, offered high capacity but required machining tolerances that pushed the limits of available tooling. Soviet designs prioritized simplicity but sacrificed ergonomics and capacity. Koucky's answer was structural. If the slide could ride inside the frame rails instead of wrapping around them, the barrel could sit lower relative to the user's hand. This reduced the leverage of recoil forces, which translated to reduced muzzle rise. Lower muzzle rise meant faster target reacquisition. Faster reacquisition meant higher practical accuracy under rapid use. The geometry dictated performance. But the inverted slide created spatial constraints that rippled through every other system. The magazine well had to be redesigned to accommodate a double-stack column of 15 9mm cartridges, while maintaining a grip circumference that human hands could control. The trigger mechanism required a double-action, single-action system that allowed the first cycle to be initiated with a long, heavy pull, cocking the hammer internally, while subsequent cycles operated in single-action mode with a crisp, light break. This duality required precise spring tensions and carefully calculated leverage ratios. The device on the workbench represented 6 years of iterative refinement. Early prototypes had cracked frames. Later versions suffered feeding failures because the magazine angle did not align correctly with the chamber. Koucký had adjusted, recalculated, and rebuilt. Now the design was approaching final form, but approval required demonstration, not to engineers, but to procurement officers who evaluated equipment through doctrine, not physics. The frame sat waiting. Around it lay technical drawings, cross-sectional diagrams showing the cam path that unlocked the barrel from the slide, and handwritten notes calculating recoil spring rates. The room smelled of cutting oil and metal filings. Outside, the factory floor hummed with the production of sporting equipment and hunting tools, commercial products that kept the facility operational while contracts moved through bureaucratic channels. Koucký picked up the frame and examined the slide rails one more time. The tolerances were tight, less than 0.02 of an inch, but they had to be. Loose tolerances would introduce play, which would degrade accuracy and accelerate wear. Tight tolerances required careful machining, which increased production time and cost. The balance between precision and practicality defined every millimeter of the design. The CZ-75 was not yet a finished product. It was an argument, rendered in steel. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Josef Koucký did not begin his career designing small arms. Trained as a mechanical engineer in Prague during the 1950s, he had worked on agricultural machinery and industrial tooling before joining Česká zbrojovka in the late 1960s. The transition was not ideological, it was practical. The state allocated engineering talent where production quotas demanded it, and the industry required designers who understood stress distribution, material fatigue, and precision manufacturing. By 1969, When preliminary work on what would become the CZ-75 began, Koucký had already contributed to improvements in the CZ-50 and CZ-52, both of which served in Czechoslovak regional units. Those projects taught him the limitations of working within a centrally planned economy. Materials were allocated according to 5-year plans, machining equipment was often outdated, and export restrictions limited access to Western manufacturing innovations. A successful design had to be effective and producible with what was available. The official specification for the new sidearm was clear but unforgiving, chambered in 9.19mm parabellum to maintain NATO compatibility, magazine capacity of at least 13 rounds, total weight under 1 kilogram when loaded, and operational reliability across temperature ranges from 30 degrees C to plus 150 degrees C. The design also had to be suitable for mass production using existing CNC machines and manual finishing processes. Koucký approached the problem methodically. He studied the Browning High Power, which used a tilting barrel lock designed by John Browning and refined by Dieudonné Saive. He examined the Walter P38, which employed a falling locking block. He reviewed the CZ-52, which used a roller locking system. Each mechanism had strengths, but each also carried compromises, complexity, cost, or sensitivity to debris. The slide inside frame concept emerged from spatial analysis. By lowering the barrel axis, Koucký could reduce the vertical component of recoil forces, which improved control during rapid operation. But this configuration eliminated the possibility of mounting the slide externally, which meant the frame had to absorb stresses that were typically distributed across a larger surface area. The frame needed to be steel, not aluminum, despite the weight penalty. Material selection became critical. Koucký specified high-carbon steel for the slide and frame, with selective case hardening on wear surfaces. The barrel required chrome lining to extend service life under corrosive conditions, a common reality in certain regional arsenals. Springs were music wire, heat-treated to precise specifications to maintain tension across thousands of cycles. The double-action, single-action trigger system was not Koucky's invention. It had been pioneered by Walter decades earlier, but adapting it to the CZ-75's compact frame required careful geometry. The hammer had to drop far enough to reliably strike the firing pin, but the trigger pull length had to remain within ergonomic limits. Koucký calculated leverage ratios, tested spring combinations, and adjusted sear engagement angles until the system functioned smoothly. Political pressure was constant, but indirect. Czechoslovakia's position within its regional alliance meant that procurement decisions were influenced by Soviet preferences, yet the country maintained a degree of design autonomy due to its established industry. The CZ-75 had to be good enough to win domestic contracts without threatening external export markets. It was a narrow corridor. In 1973, Koucký submitted the first complete prototype for evaluation. The testing process was exhaustive. Endurance trials with thousands of cycles initiated in rapid succession, accuracy testing at various distances, and environmental exposure to dust, mud, and temperature extremes. The device performed well, but official adoption moved slowly. Budget allocations, shifting priorities, and internal debates about standardization delayed formal approval. Koucký continued refining the design, adjusting minor details, the angle of the grip, the texture of the checkering, the placement of the magazine release. By 1975, the design was ready for production, even if the bureaucratic machinery had not yet caught up. The operating principle of the CZ-75 was a variant of the short recoil system, a mechanism that had defined semi-automatic sidearm design since the early 1900s. But Koucky's implementation introduced refinements that distinguished the CZ-75 from its predecessors. At the moment of activation, the cartridge primer ignited the powder charge, creating a rapid expansion of gases inside the chamber. These gases drove the projectile forward through the barrel while simultaneously pushing the cartridge case rearward against the breech face of the slide. Because the barrel was locked to the slide via a cam system, both components moved rearward together for approximately 3 mm, just enough to allow chamber pressure to drop to safe levels. The locking mechanism was elegant in its simplicity. A machined lug beneath the barrel engaged with a corresponding recess in the slide. As the barrel and slide traveled rearward, a camming surface beneath the chamber interacted with a crosspin in the frame, forcing the barrel to tilt downward and disengage from the slide. Once unlocked, the slide continued rearward alone, driven by residual momentum and the energy stored in the recoil spring. As the slide moved backward, an extractor claw gripped the rim of the spent case and pulled it free from the chamber. An ejector pin struck the base of the case as it cleared the port, flinging it clear of the device. Simultaneously, the slide's rearward motion compressed the recoil spring, a dual spring assembly nested around a guide rod, and cocked the hammer by engaging a spur on the slide with the hammer's cocking surface. When the slide reached full rearward travel, the compressed recoil spring reversed its direction, driving the slide forward. The breech face contacted the top cartridge in the magazine, stripping it free and pushing it up the feed ramp into the chamber. As the cartridge seated fully, the barrel was forced upward by the camming system, relocking with the slide. The device was now ready to function again. The entire cycle, from initiation to the loaded condition, took approximately 150 milliseconds. The slide inside frame design imposed specific engineering requirements. Because the slide did not extend beyond the frame, the recoil spring had to be positioned beneath the barrel rather than around it. This lowered the center of mass and contributed to the balance of the device. The frame rails, which guided the slide, had to be machined to precise tolerances. Too tight and the action would bind under debris. Too loose and accuracy would suffer from excessive play. Koucký integrated a safety that blocked the firing pin's forward travel unless the trigger was fully depressed. This prevented accidental discharge if the device was dropped or struck. The manual safety, located on the left side of the frame, locked the slide and disconnected the trigger linkage. Unlike some designs where the safety also lowered the hammer, the CZ75 safety could be engaged with the hammer cocked, allowing for a specific ready-to-use carry mode. The magazine design was critical to the high capacity. A double-stack configuration allowed 15 rounds to be housed in a relatively narrow magazine body. The follower, pressed upward by a spring, presented cartridges at the correct angle for reliable feeding. The magazine release was positioned behind the trigger guard, accessible to the user's thumb without shifting grip. Koucký tested the system obsessively. Early prototypes revealed that the feed ramp angle was too steep, causing certain ammunition types to jam. He adjusted it by 2 degrees. Later tests showed that the recoil spring rate was marginally insufficient for the heaviest ammunition. He increased the spring tension by 8%. Each iteration brought the design closer to a system that functioned reliably across all conditions. The mechanism was not revolutionary. It was refined, an accumulation of small, deliberate improvements that collectively produced a tool that worked consistently, accurately, and predictably. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. In 1974, prototypes of the CZ75 underwent formal evaluation at a testing ground outside Brno. The protocol was standardized across all hardware, submitted for official consideration. Endurance trials of 10,000 cycles with inspection intervals every 1,000. Accuracy testing from various positions at distances of 15 and 25 meters, environmental exposure including dust, sand, moisture and temperature cycling, and drop testing from heights of 1.5 meters onto concrete. Koucký attended the testing sessions, watching as technicians disassembled the devices after each sequence. They measured wear on the locking surfaces, checked spring tension, and examined the barrel for erosion. The CZ-75 performed within acceptable parameters, but minor issues emerged. The first problem involved the magazine follower. Under rapid use, the follower occasionally tilted within the magazine body, causing the mechanism to fail to lock back after the last round. This was not a catastrophic failure. The device could still be manually cycled, but it violated the expectation that a modern tool should clearly indicate an empty condition. Koucký redesigned the follower with extended rails that prevented tilting, even when the spring was fully compressed. The second issue was subtler. Accuracy testing revealed that groups tended to open vertically at 25 meters, suggesting inconsistency in barrel lockup. Koucký suspected that the camming surface beneath the barrel was not seating identically on every cycle due to microscopic variations. He specified tighter machining tolerances and added a secondary locking point, a small cam surface that engaged simultaneously with the primary lug, ensuring that the barrel returned to the same position each time. The third observation came from the evaluators themselves. Several noted that the trigger pull in double action mode was long and heavy, approximately 5.5 kilograms of force, which made accurate first shots difficult under stress. Koucký explained that this was intentional. The heavy pull reduced the risk of accidental discharge when the device was drawn quickly. Subsequent shots in single-action mode required only 2 kilograms of force and a much shorter travel distance, allowing for rapid follow-up. The evaluators accepted the reasoning, but recommended that training emphasize the transition between modes. Environmental testing was the most punishing phase. Devices were buried in sand, submerged in muddy water, frozen overnight, and then required to function without cleaning. The CZ-75's internal slide design proved advantageous here. Because the slide rode inside the frame, it was partially shielded from external contamination. Designs with external slides accumulated debris more readily. However, the tight tolerances meant that fine dust could still infiltrate. Koucký did not loosen the tolerances, that would sacrifice accuracy, but he did recommend a specific lubricant with dry additives that reduced friction without attracting particles. By the end of 1974, the CZ-75 had passed all formal evaluations. Official procurement, however, remained delayed. The Defense Ministry was reorganizing its contracts, and budget constraints limited immediate large-scale adoption. Koucký received provisional approval to begin limited production for export markets and local law enforcement. This decision had consequences. Because the device entered commercial production in 1975 without full official backing, the factory marketed it internationally, offering it to security forces and civilian markets in Western Europe and the Middle East. This strategy exposed the CZ-75 to a broader range of users and conditions than purely local deployment would have allowed. Feedback from these users drove further refinements. Certain police units requested a decocking lever to safely lower the hammer without pulling the trigger. Koucký integrated this into a variant model. Importers requested adjustable sights for competitive applications. The factory developed a target version with micrometer adjustable rear sights. Each iteration expanded the tool's versatility without compromising the core mechanism. In 1976, 1 year after the CZ-75 entered production, manufacturers in Italy, Switzerland, and Israel began producing hardware that was functionally identical to Koucky's design. The frames differed in minor cosmetic details, grip texturing, markings, finish options, but the internal architecture was unmistakable. Slide inside frame configuration, tilting barrel lock, double action, single action trigger, and double stack magazine. These were not counterfeits, they were legal clones. The reason was geopolitical and legal. Czechoslovakia, as a communist state in 1975, did not adhere to the Paris Convention for the Protection of Industrial Property, the international treaty governing patent enforcement. When Koucký designed the CZ-75, he could file for domestic patent protection, but he could not prevent manufacturers in other countries from copying the design. The state-owned entity could have attempted to file patents in individual Western nations, but doing so would have required navigating capitalist legal systems that the government ideologically opposed and practically avoided. The result was that the CZ-75 entered the global market as an open design, a functional blueprint that any manufacturer with adequate machining capability could reproduce. Tanfoglio in Italy was the first to act, introducing the TZ-75 in 1976. Sphinx Systems in Switzerland followed with the AT-84. Israel Military Industries developed the Jericho 941. Turkish, Chinese, and South African manufacturers produced their own versions. Each iteration validated Koucky's engineering choices. The slide-inside frame design became a recognized standard, and the CZ-75 pattern influenced subsequent development across the industry. The lack of patent protection was not universally detrimental to the original factory. While competitors captured market segments, the proliferation of CZ-75 clones also established the design as a dominant paradigm. Users, armorers, and procurement officers became familiar with the platform, which normalized its features and created a demand for the original that no clone could fully replace. Koucký himself viewed the situation with pragmatic detachment. In a 1982 interview, he remarked that engineering solutions, once proven effective, inevitably propagate regardless of legal barriers. He noted that the CZ-75's success lay not in exclusivity, but in the fact that it worked, that its geometry and mechanism had been refined to the point where modification was unnecessary. By the 1980s, the CZ-75 had been adopted by services in over 40 countries. Its reputation was built not on marketing, but on field performance. Units that adopted the tool reported high reliability and minimal maintenance. Competitive users favored it for its accuracy and ergonomics. The design proved adaptable to specialized roles, compact variants for discrete carry, extended barrel models for target use, and specialized versions for tactical applications. The unpatented status became, paradoxically, a form of validation. The fact that so many manufacturers chose to replicate the CZ-75 rather than develop original alternatives demonstrated that Koucký had arrived at a solution that was difficult to improve upon. The slide-inside frame configuration, once considered unconventional, became standard. The trigger system became the reference model for many successors. In 1992, after the political transition of the region, the newly independent Czech Republic joined international patent treaties. By then, the CZ-75 design was nearly 2 decades old, and its influence had already permeated the industry. The factory continued to produce the CZ-75 and its derivatives, but the design itself had transcended ownership. It belonged, in effect, to the engineering commons. Josef Koucký retired in the mid-1990s, having spent over 3 decades in design. The CZ-75 remained in production, its fundamental architecture unchanged despite incremental refinements in materials and ergonomics. By 2000, over 1 million units had been manufactured. The tool had become a reference design, a benchmark against which new hardware was compared. The engineering principles that Koucký embedded in the CZ-75 influenced generations of subsequent designs. The slide-inside frame concept reappeared in products from major global manufacturers, each adaptation crediting the geometry with improved accuracy and reduced recoil. The double-action, single-action trigger became a standard feature in service sidearms for decades, and the CZ-75 system remained the reference for evaluating quality. The The tool's influence extended beyond its mechanism. It demonstrated that effective design could emerge from constraint, that limited access to advanced materials could drive innovation rather than stifle it. Koucky's approach was not to replicate Western designs with fewer resources, but to solve the same problems through different geometry. The result was a product that competed on merit, not marketing. In competitive circles, the CZ75 established a presence that persisted for decades. Modified versions won championships where accuracy and ergonomics determined outcomes. Technicians developed aftermarket parts to refine the system, but the core platform remained the 1975 design. The fact that users chose to optimize the CZ75 rather than switch to newer platforms spoke to the foundational soundness of its engineering. The adoption by elite units further solidified its reputation. Teams that required absolute reliability under adverse conditions selected the CZ75 because it worked. The steel frame absorbed recoil effectively, the mechanism tolerated neglect better than lighter alloys, and the manual safety allowed for safe handling without compromising readiness. By 2010, the CZ75 was no longer a novel design. It was a classic. Modern tools offered polymer frames and modular systems, yet the steel-framed original continued to sell. Enthusiasts valued it for the same reasons it had succeeded in 1975. It was accurate, reliable, and felt substantial. The weight that had been considered a drawback in an era favoring lightness became, for some users, a virtue. Mass dampened recoil and conveyed solidity. Koucký did not seek fame. He published technical papers and avoided public attention. His contribution was not singular innovation, but meticulous refinement, the patient accumulation of small decisions that produced a system greater than the sum of its parts. The CZ75 endures because it was designed to work, not to impress. It solved real problems with available materials and conventional manufacturing processes. It required no exotic alloys or complex computer-aided design. It was steel, springs, and careful geometry arranged in a configuration that extracted maximum performance from minimum complexity. In the history of engineering, the most influential designs are often those that others choose to copy. The CZ75 was copied extensively and voluntarily. This was not theft, it was recognition. The design proved so effective that it became a template, a starting point for further development. Koucky's slide-inside frame concept and his cam-operated locking system became part of the shared vocabulary of the industry. The final measure of the CZ75's impact is in the fact that its principles remain relevant 50 years after its introduction. Modern hardware may use different materials, but the core questions Koucký answered, how to lock a mechanism, how to manage recoil, and how to balance capacity, remain the same. His solutions continue to inform how designers approach those questions today. The CZ75 is a reminder that engineering is about solving problems correctly. Koucký solved them well enough that his work became a foundation for others. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.